There's a moment in the life of every star when it burns its last fuel, when the light it's poured into the universe for billions of years finally flickers out. But here's the astonishing part: even as the cosmos itself cools and expands into endless darkness, light doesn't just vanish, it fights, it escapes, and in its final journey, it carries secrets about the very fabric of reality. What if I told you that the last whispers of light from a dying universe could rewrite our understanding of time, space, and existence itself? This isn't just a thought experiment, it's the inevitable future of everything we know, and it's unfolding right now, in the slow, silent dance of galaxies drifting apart. Think about the light you see every day, the warmth of the sun, the glow of a street lamp, the shimmer of stars on a clear night. All of it is fleeting. Because the universe has an expiration date. Billions of years from now, stars will burn out, black holes will evaporate, and space will stretch into an infinite, icy void. Yet, against all odds, light will still be there, threading its way through the emptiness. How and what can these escaping photons tell us about the laws of physics, the nature of time, or even the possibility of something beyond the end? The answers lie in the strange, counterintuitive behavior of light itself, a behavior that defies our everyday intuition and challenges the very limits of human understanding. This is more than just a story about the death of the cosmos. It's a revelation about resilience, about how even in the face of total annihilation, information, the imprint of everything that ever was, finds a way to endure. The light that escapes a dying universe isn't just a farewell, it's a message, a cosmic breadcrumb leading us toward truths we're only beginning to grasp. So buckle up. Over the course of this journey, we'll unravel the physics behind light's great escape, explore what it means for the fate of reality, and maybe, just maybe, catch a glimpse of what lies beyond the end of everything. Because when it comes to the universe, even in its final moments, the story isn't over, it's just beginning. Light is the universe's oldest storyteller. Every photon that reaches your eyes has traveled across space and time, carrying with it a fragment of history, a snapshot of the cosmos as it once was. When you gaze at the stars, you're not just seeing points of light, you're peering into the past, witnessing events that unfolded millions, even billions of years ago. But light's role goes far beyond mere illumination. It's a cosmic courier encoding the secrets of distant galaxies, the birth of stars, and the very fabric of spacetime itself. Consider this: light doesn't just move through the universe, it interacts with it. Every gravitational warp, every ripple in spacetime leaves its mark on a photon's journey. When light passes near a massive object like a galaxy or a black hole, its path bends, its wavelength stretches or compresses, and its very nature is altered. This phenomenon, called gravitational lensing, isn't just a curiosity, it's a tool. Astronomers use it to map invisible dark matter, to peer around cosmic corners, and even to test Einstein's theory of relativity. Light, in other words, doesn't just show us the universe, it reveals its hidden machinery. Now imagine the far future, when the universe has expanded beyond recognition, when galaxies are so far apart that their light can no longer bridge the gap. Even then, light won't simply surrender. As space stretches, photons stretch with it, their wavelengths growing longer and fainter, like echoes fading into silence. But here's the twist: that fading light still carries information. It's a fingerprint of the universe's expansion, a record of how space itself has evolved over eons. By studying this light, its redshift, its dispersion, its very persistence, we can uncover clues about the fate of everything. Quantum mechanics adds another layer of mystery. At the smallest scales, light behaves less like a wave and more like a particle, a bundle of energy that defies classical intuition. Photons can become entangled across vast distances, their fates intertwined in ways that challenge our understanding of cause and effect. In a dying universe where distances grow incomprehensibly vast, these quantum properties might hold the key to how information, perhaps even the memory of the cosmos itself, endures. So when we talk about light escaping a fading universe, we're not just talking about physics. We're talking about resilience. We're talking about how the universe, even in its final act, refuses to let its story vanish without a trace. The light that lingers in the void isn't just a relic. It's a testament to the unbreakable bond between energy, space, and time. And as we decode its whispers, we may just find that the end of everything is also a beginning, a doorway to truths we've only begun to imagine. Edwin Hubble peered through his telescope in the 1920s and saw something that shattered humanity's understanding of the cosmos. Galaxies weren't just floating in space. They were racing away from us, their light stretched into longer, redder wavelengths as space itself expanded between us and them. This redshift wasn't just a curiosity, it was proof that the universe wasn't static. It was alive, growing, stretching the very fabric of reality with every passing moment. And if space could stretch, what did that mean for the light trapped within it? Imagine a photon emitted by a dying star billions of years ago, traveling across the cosmos toward us. As it journeys, the space through which it moves isn't static. It's expanding like a loaf of bread rising in the oven. The photon's wavelength stretches along with it, shifting from visible blue or yellow into the red, then into infrared, and eventually into radio waves so faint they're nearly undetectable. Given enough time, even the most brilliant beacon in the universe could fade beyond recognition. Its light stretched so thin it dissolves into the background hum of spacetime itself. But here's where things get strange. Light doesn't just give up. Even as the universe expands at an accelerating rate, pushing galaxies beyond the horizon of observation, those photons keep traveling. They're like marathon runners in a race where the finish line keeps moving farther away, yet they press on, carrying their precious cargo of information. And this raises a profound question. If the universe expands forever, will there come a time when all light is stretched beyond detection? Will the cosmos one day go dark, not because the stars have burned out, but because their light can no longer reach us? The answer lies in the delicate balance between expansion and persistence. While most distant light will eventually redshift into oblivion, some photons will always remain just within the edge of detectability, a ghostly afterglow of a universe that once was. And these stubborn holdouts might be the key to understanding the deepest mysteries of reality. They could carry clues about dark energy, the mysterious force driving the universe's accelerating expansion, or even hint at the existence of dimensions beyond our own. What's truly remarkable is that light's struggle against the expanding universe isn't just a cosmic quirk, it's a mirror of our own quest for understanding. Just as photons fight to be seen across unimaginable distances, we strain to decipher their fading whispers, piecing together the story of existence one redshifted signal at a time. The light that escapes a dying universe isn't just a relic. It's a challenge, a puzzle waiting to be solved. And as long as there are photons left to observe, the story of the cosmos isn't over, it's still being written. Dark energy is the universe's silent architect, shaping the fate of everything we see and everything we can't. Imagine an invisible hand pushing space itself apart, accelerating the expansion of the cosmos with each passing moment. This isn't science fiction, it's the reality we live in. In the late 1990s, astronomers made a discovery that turned cosmology upside down. The universe wasn't just expanding, it was doing so faster and faster, as if some unseen force were stretching spacetime itself. They called this force dark energy, and to this day it remains one of the greatest mysteries in physics. Here's why it matters for light's escape. As dark energy drives galaxies apart, it doesn't just create distance, it rewrites the rules of the cosmic game. Think of space as a vast ocean with galaxies as ships sailing away from one another. Normally, you'd expect those ships to slow down over time, like objects drifting apart in calm waters. But dark energy is like a relentless current, speeding them up instead. For light trying to cross that ocean, the challenge becomes unimaginable. The space between galaxies stretches faster than the photons can traverse it, leaving some light forever stranded, redshifted into oblivion. Yet, paradoxically, some photons will make it. They're the survivors, the ones emitted just close enough, just early enough to outrun the accelerating tide. What does this mean for the universe's ultimate fate? If dark energy continues unchecked, it won't just isolate galaxies, it will dismantle them. Over trillions of years, the accelerating expansion could tear apart stars, planets, even atoms themselves in a hypothetical event called the Big Rip. But long before that, dark energy will have already reshaped the cosmic landscape into something unrecognizable. The night sky, once filled with the glow of distant galaxies, will fade to black. The only light left will be from the rarest, most tenacious photons, the ones that slipped through the cracks before the door slammed shut. Yet even in this bleak scenario, dark energy offers a strange kind of hope. Because it ensures that some light always escapes, carrying with it the fingerprints of the universe's history. These photons become time capsules, preserving information about the cosmos as it was before the Great Isolation. By studying them, we might uncover clues about dark energy's true nature, whether it's a constant force, as Einstein's cosmological constant suggested, or something more dynamic, like a field that evolves over time. The irony is profound. The same force that's tearing the universe apart is also, in a way, preserving its memory. Dark energy doesn't just accelerate the end, it sculpts the legacy. And as we piece together its secrets, we're not just learning about the fate of light in a dying cosmos. We're glimpsing the deeper laws that govern reality itself. Because in the end, the story of dark energy isn't just about how the universe dies. It's about how, even in its final act, it refuses to let its story be forgotten. Entropy is the universe's silent clock, ticking relentlessly toward a state of perfect stillness. It's the reason your coffee cools, the reason stars exhaust their fuel, and ultimately, the reason the cosmos will one day fade into darkness. But this isn't a dramatic explosion or a violent collapse, it's a slow, inevitable unraveling, where energy becomes so evenly distributed that nothing can stir, no work can be done, and no new light can be born. This is the heat death of the universe, the ultimate triumph of disorder over structure. Picture a campfire burning down to embers. At first, the flames are bright and lively, but over time, the heat spreads outward, dissipating into the cold night air until only a faint warmth remains. Now imagine that process stretched across trillions of years, applied to every star, every galaxy, every flicker of energy in existence. That's heat death, not an absence of energy, but energy so diffuse it's useless. No more temperature differences, no more gradients to drive motion or life, just a vast, featureless sea of sameness. Yet even in this frozen eternity, light refuses to disappear entirely. Photons, those tiny packets of energy, will continue their endless journeys, redshifted to wavelengths longer than the universe itself. They'll be the last witnesses to everything that once was, carrying echoes of supernova, quasars, and civilizations long since turned to dust. But why? Because light, unlike matter, doesn't decay. It doesn't succumb to entropy's grasp. A photon emitted today could, in theory, travel forever, or at least until it's stretched so thin it becomes indistinguishable from the cosmic background. This raises a haunting question. If the universe reaches heat death with all its energy irreversibly scattered, what's the point of those wandering photons? The answer lies in the subtle interplay between time and information. Light doesn't just illuminate, it encodes. Every photon that escapes a dying star, every ripple of radiation fleeing a black hole's evaporation, carries data about the universe's history. In a cosmos where all else has faded to equilibrium, these photons become the last threads connecting the future to the past. There's a profound beauty in this. Even as the universe succumbs to entropy, even as structure dissolves into chaos, light endures. It's a testament to the indomitable nature of information, the idea that some things, whether by the laws of physics or the stubbornness of existence, cannot be erased. The heat death may be inevitable, but it's not the end of the story. It's merely the stage upon which light's final act plays out, a whisper in the dark reminding us that even in oblivion, something remains. Black holes, those cosmic voids where gravity is so strong not even light can escape, might seem like the last place you'd expect to find light in a dying universe. But here's the twist, even these monsters of darkness don't last forever. Thanks to Stephen Hawking's groundbreaking work, we now know black holes aren't the eternal prisons they appear to be. Over unimaginable spans of time, they slowly leak energy, radiating away their mass in a faint glow known as Hawking radiation. This means that long after the last stars have burned out, long after galaxies have drifted apart into the void, black holes could become the final beacons in an otherwise lightless cosmos. So how does light escape the inescapable? It all comes down to quantum mechanics. At the very edge of a black hole's event horizon, pairs of particles and antiparticles constantly flicker in and out of existence. Normally, they annihilate each other instantly, but when this happens right at the boundary of a black hole, one particle can fall in while the other escapes, stealing a tiny bit of the black hole's energy in the process. Over trillions upon trillions of years, this slow trickle of particles adds up, causing the black hole to shrink until poof, it vanishes in a final burst of radiation. That final burst is key, because if black holes are the last structures standing in a heat-dead universe, their evaporation could be the last significant event in cosmic history. Imagine a universe so old that time itself has lost meaning, where space is colder than absolute zero, and the only thing left is a sparse collection of ancient black holes, each glowing faintly as they evaporate. The last light in existence wouldn't come from stars or galaxies, it would come from these dying titans, their Hawking radiation painting the void with one final, ghostly shimmer. But here's what's even more fascinating. That last whisper of light might carry more than just energy. It could encode information about the black hole's history, what fell into it, how it formed, even clues about the laws of physics at the edge of reality. This ties into one of the biggest mysteries in theoretical physics, the black hole information paradox. If information can't truly be destroyed, then somehow, someway, the secrets swallowed by black holes must eventually resurface. Hawking radiation could be the universe's way of ensuring nothing is ever truly lost. Of course, this raises a haunting question. If black holes are the last sources of light, what happens when they're gone? When the final black hole evaporates, will the universe truly be empty, or will some trace of its existence linger? Some theories suggest that even then, quantum fluctuations or the remnants of Hawking radiation could persist, a faint, eternal afterglow of a cosmos that once was. Others propose that new universes could bubble into existence from the energy left behind. One thing is certain: black holes, the darkest objects in the universe, might hold the key to its final flicker of light. And in that flicker, we might just find the answers to questions we haven't even thought to ask yet. Because even at the end of everything, the universe refuses to go quietly. It leaves behind a message written in the last, fading glow of dying black holes. Quantum tunneling defies everything we think we know about barriers. In the everyday world, if you throw a ball at a wall, it bounces back simple physics. But in the quantum realm, particles like electrons and photons play by different rules. There's a chance, however small, that they can phase through that wall as if it weren't even there. It's not magic, it's a fundamental quirk of reality, where particles exist as probability waves until measured, slipping through energy barriers like ghosts passing through doors. Now imagine the universe in its final throes, collapsing under its own gravity. Space contracts, galaxies merge, and the cosmic horizon shrinks. Light, racing outward, finds itself trapped by the crushing weight of spacetime itself, or so it seems. Quantum tunneling offers a loophole. Even as the universe closes in, photons could exploit this strange effect, vanishing through barriers that classical physics says should be impenetrable. They wouldn't break the rules, they'd bend them, emerging on the other side like cosmic escape artists. This isn't just theoretical. We've seen quantum tunneling in action here on Earth in semiconductors, nuclear fusion, even the chemistry of life itself. Enzymes use it to speed up reactions, solar cells harness it to capture energy. But on a cosmic scale, tunneling could mean the difference between light being snuffed out forever or slipping free to tell its story. Think of it as the universe's emergency exit, a hidden pathway woven into the fabric of physics itself. There's a poetic symmetry here. Just as the universe began with quantum fluctuations, tiny particles tunneling into existence from nothing, so too might it end with particles tunneling out, carrying traces of what once was. The light that escapes wouldn't just be random noise, it could encode the universe's final state, a message in a bottle tossed into the void. And if we, or some far future intelligence, could decode it, we might find answers to questions we haven't even thought to ask. Of course, this raises a tantalizing question. If light can tunnel out of a collapsing universe, could something else follow? Could information, or even structure, find a way to persist beyond the end? Some theories suggest that tunneling might not just be an escape route but a bridge, a thread connecting one dying cosmos to the birth of another. It's a dizzying thought, hinting that even in oblivion, the universe might leave a backdoor open, ensuring its story never truly ends. So while quantum tunneling might seem like an obscure footnote in physics textbooks, in the grand saga of the cosmos, it could be the hero of the final act. The universe's last light might not fade into darkness after all, it might just step through an invisible door, leaving us with one final, breathtaking revelation, that even at the edge of existence, the rules are never quite what they seem. Einstein taught us that space isn't just an empty stage where light moves in straight lines, it's a dynamic fabric, warped and twisted by the mass of stars, galaxies, and even invisible dark matter. This curvature doesn't just bend the paths of planets, it bends light itself, redirecting photons like a cosmic funhouse mirror. But what happens to this delicate dance of spacetime and light when the universe reaches its twilight, when stars fade and black holes evaporate? The answer lies in the slow unraveling of gravity's grip. Picture a marble rolling across a stretched bedsheet. The heavier the objects placed on that sheet, the deeper the dips they create, and the more the marble's path curves. Now imagine removing those objects one by one. The sheet gradually flattens and the marble's path straightens. In the dying universe, something similar happens to spacetime. As matter disperses, stars burning out, black holes radiating away, the fabric of reality loses its wrinkles. The once intricate web of gravitational wells and peaks smooths into a vast, featureless plain. And light, no longer tugged by massive objects, travels straighter than ever before. But here's the catch: even in this flattened cosmos, light's journey isn't as simple as a straight line. Space-time curvature doesn't vanish entirely. The echoes of ancient structures, superclusters that once spanned millions of light-years, the ghostly remnants of black holes, leave faint imprints on the fabric of reality. These lingering distortions act like cosmic signposts, subtly steering the last escaping photons. The light that reaches the far future won't just be stretched and dimmed by expansion. It will carry the faintest whispers of a universe that once bent it to its will. There's another layer to this: dark energy, the mysterious force accelerating the universe's expansion, doesn't just stretch space, it may also alter its curvature over time. Some theories suggest that as dark energy dominates, it could create a new kind of large-scale curvature, a gentle warp across the entire cosmos. Light traveling through this altered spacetime would face a different set of rules, its path shaped not by local masses but by the universe's overarching geometry. It's like swapping a winding mountain road for a slow, endless slope. The journey changes, but the destination remains just as uncertain. What does this mean for the last light escaping the universe? It means that even in the bleakest, most distant future, no photon's path is truly random. Every ray carries the history of spacetime's curvature, a record of how gravity's fingerprint faded but never fully disappeared. And if we could decode that record, we might uncover secrets about the universe's structure that are invisible to us today. The final flickers of light won't just be relics of the past, they'll be maps tracing the slow unraveling of spacetime itself. So while the dying universe may seem like a static, empty void, it's anything but. Spacetime curvature, though fading, ensures that light's last journey is still a story, one written in the subtle bends and twists of a fabric that never quite lets go. And in that story, we might just find the ultimate answers to how the cosmos lived, how it died, and what, if anything, comes next. The cosmic microwave background is the oldest light we can see, a whisper from the universe's fiery birth, stretched and cooled over 13.8 billion years into a faint glow that permeates all of space. It's the afterimage of the Big Bang, a snapshot of the cosmos when it was just 380,000 years old, hot and dense enough to glow like the surface of a star. Today, that light has redshifted into microwaves, invisible to our eyes but detectable as a static hiss in radio telescopes. It's the universe's baby picture, and it carries secrets about how everything began. But as the cosmos expands toward its eventual cold, dark fate, what happens to this primordial light? Will it be the last survivor, flickering in the void long after everything else has faded? Or will even this relic succumb to the relentless march of entropy? To understand the cosmic microwave background's fate, we need to rewind to its origins. In the universe's first moments, space was a seething plasma of particles and energy, so dense that light couldn't travel far before colliding with an electron. But as the cosmos expanded and cooled, electrons and protons combined into atoms, clearing the fog and allowing photons to stream freely for the first time. That moment of liberation created the light we now detect as the cosmic microwave background. It's been traveling ever since, stretched by the expansion of space, its energy diluted but never fully extinguished. Fast forward trillions of years, the universe has expanded so much that galaxies beyond our local group have vanished over the horizon. their light stretched beyond detection. Stars have burned out, black holes have evaporated, and the cosmos is a vast, dark expanse. Yet the cosmic microwave background persists diminished, redshifted into radio waves with wavelengths longer than the observable universe itself, but still present. It's the last echo of creation, a signal so faint it would take unimaginably sensitive instruments to detect. But here's the twist, even this ancient light isn't eternal. As space continues to expand, the cosmic microwave background's photons will stretch further, their energy dwindling until they dissolve into the quantum noise of spacetime itself. The process mirrors what happens to all light in an accelerating universe, but with one key difference. This isn't just starlight fading. It's the universe's founding signal finally going silent. The moment the last whisper of the Big Bang vanishes marks the true end of the cosmic story, a final severing of our tether to the beginning. Yet there's a strange comfort in this. The cosmic microwave background has been our bridge to the infant universe, a Rosetta Stone for decoding the laws of physics. Its gradual disappearance isn't just an ending, it's a reminder that even the most enduring echoes fade, and that the universe's story, like all stories, has a final page. But until that page turns, this ancient light remains, a testament to the fact that from the moment of its birth, the cosmos has been fighting to be remembered. And in that fight, it's left us clues not just about how it began, but about how, one distant day, it will end. Dark matter is the universe's silent architect, shaping everything from the smallest galaxies to the largest cosmic webs, yet we've never seen it directly. It doesn't emit, absorb, or reflect light, making it utterly invisible to our telescopes, but its presence is undeniable. Without dark matter's gravitational glue, galaxies would fly apart, and the universe as we know it wouldn't exist. So what happens to this mysterious substance as the cosmos approaches its final act? And more intriguingly, how will its invisible hand steer the last escaping light? Think of dark matter as a cosmic scaffold, an unseen framework holding the universe together. While stars and gas swirl within galaxies, dark matter forms vast, diffuse halos around them, its gravity dictating the motion of everything we can see. Even as galaxies fade and stars burn out, these halos persist, their gravitational pull lingering long after visible matter has dissipated. But here's the catch: dark matter isn't static. It interacts with itself and with space-time in ways we're still struggling to understand. Some theories suggest it could decay over eons, releasing energy or even new particles. Others propose that dark matter might clump into exotic structures, like invisible black holes or sprawling filaments colder than the void itself. Now imagine the far future, when the universe is a graveyard of dead stars and evaporated black holes. Dark matter's halos, though weakened, would still warp spacetime, bending the paths of any surviving photons like a hidden lens. Light escaping this barren cosmos wouldn't travel in straight lines. It would weave through the ghostly remnants of dark matter's influence, carrying subtle distortions that betray its presence. These distortions could be the last fingerprints of dark matter, imprinted on the fading light like a signature on a farewell letter. But there's another possibility, one that's even stranger. If dark matter particles interact with each other, even faintly, they might emit their own form of radiation as the universe cools. This dark light wouldn't be visible in any conventional sense, but it could leave traces in the spectrum of the final photons, a whisper of something beyond ordinary physics. Detecting such a signal would require instruments far beyond anything we have today, but the mere possibility raises a tantalizing question. Could the last light in the universe carry not just the story of visible matter, but the secrets of the unseen? The irony is profound. Dark matter, which has hidden from us since the dawn of time, might finally reveal itself in the universe's dying moments. Its gravitational echoes, its possible decays, its subtle imprints on escaping light, all of these could be clues waiting in the far future, messages from an invisible world that shaped everything. And if we could decode them, we might finally understand the true nature of the cosmos's hidden skeleton, because even in the end, dark matter refuses to let the universe fade quietly. It leaves behind riddles written in the language of gravity and light, waiting for someone or something to read them. Time bends in the presence of immense gravity, stretching moments into eternities near black holes or across the vast distances of an expanding universe. For the last photons fighting their way free, this distortion becomes more than just a curiosity, it's their reality. Picture a single beam of light emitted near a black hole's event horizon, where gravity is so intense that time slows to a crawl. From our perspective, that photon might take years just to inch away, its wavelength stretching like taffy as it battles the pull of spacetime. But for the photon itself, time doesn't pass at all. In its frame of reference, the journey is instantaneous, a blink between emission and escape, if escape even happens at all. Now zoom out to the cosmic scale. As the universe expands, galaxies recede faster than light can bridge the gaps, creating horizons beyond which no signal can reach us. For observers in the far future, this means the light from distant stars won't just fade, it'll freeze. The photons that do manage to arrive will be stretched into lower and lower energies, their signals slowed by the expansion of space itself. Imagine watching a star's final pulse of light not as a swift flicker, but as a drawn-out sigh, a single note played so slowly it spans millennia. Time dilation transforms the cosmos into a gallery of slow-motion relics, each photon a fossil of events long past. But here's the mind-bending part. For those future observers, the universe's history won't just recede, it'll fracture. Light from different eras will arrive at wildly different rates, scrambling the timeline of cosmic events. A supernova that erupted billions of years earlier might appear frozen mid-explosion, its light smeared across eons. The last visible stars won't vanish in a clean sequence. They'll linger like ghosts, their final moments stretched into an infinite fade. For any civilization witnessing this, the universe's story won't unfold, it'll dissolve, each chapter bleeding into the next until the narrative itself becomes unrecognizable. And yet, within this distortion lies a paradox. While time slowing makes the universe seem static to a far future observer, it also preserves information that would otherwise be lost. Those infinitely redshifted photons carry data about the conditions of their birth, locked in their stretched wavelengths like messages in amber. If you could decode them, you might reconstruct the universe's youth from its dying light, a cosmic archaeology of the impossible. This duality, time's cruelty and its generosity, reveals something profound about the universe's end. Even as it stretches into silence, it refuses to let go of its past. The light that escapes a dying cosmos isn't just a farewell, it's a testament to time's stubborn grip on existence. And for those who know how to listen, it whispers a final, haunting truth, that the end of everything is also a kind of memory, etched into the fabric of space-time itself. Quantum mechanics tells us something astonishing information. The fundamental blueprint of reality can never truly be destroyed, not by black holes, not by entropy, not even by the death of the universe itself. This principle, known as unitarity, means every particle, every interaction, every event leaves an indelible mark on the cosmos. So when we talk about the last light escaping a dying universe, we're not just talking about fading energy, we're talking about the potential for that light to carry the entire history of existence, encoded in ways we're only beginning to unravel. Think of it like this: every photon emitted by a star, reflected by a planet, or bent by a black hole carries a tiny piece of data, its wavelength, its polarization, its path through spacetime. Alone, it's just noise, but collectively, these photons form a cosmic archive, a record of every gravitational ripple, every collision, every transformation the universe has ever undergone. The challenge isn't whether the information exists, it's whether we could ever piece it together. Imagine trying to reconstruct a symphony from a single note played every 1,000 years. The data is there, but the scale is staggering. This is where the paradox deepens. If the universe's expansion stretches light beyond recognition, redshifting it into near nothingness, how could any meaningful information survive? The answer might lie in quantum entanglement, the eerie phenomenon where particles remain connected across vast distances, their properties linked no matter how far apart they drift. Entangled photons could preserve correlations, subtle relationships that outlast the stretching of spacetime itself. Even as individual photons fade, their quantum connections might persist, like invisible threads holding together the torn pages of a book. But decoding this quantum manuscript would require technology beyond our wildest dreams. Picture a civilization in the far future, surrounded by a universe so dark and cold that the only light left is the faint afterglow of long-dead stars. To extract information from these photons, they'd need instruments capable of measuring quantum states with impossible precision, untangling eons of redshift and distortion. It's like trying to read a letter that's been burned, soaked, and faded, except the letter is written in the language of physics itself. Yet there's a glimmer of hope. Some theories suggest that the universe's final photons won't just be random noise. They'll form patterns, echoes of the large-scale structures that once defined the cosmos. The way light clusters, the way it's polarized, even the way it flickers could reveal traces of ancient galaxy clusters, the fingerprints of dark matter, or the echoes of inflation's first moments. It wouldn't be a perfect record, but it might be enough to reconstruct the broad strokes of cosmic history. The real question isn't just whether the information exists, it's whether anyone will be left to read it. In a universe destined for heat death, where time stretches into meaningless eternity, the very act of observation might become impossible. But if life, or some form of intelligence, finds a way to endure, the last light could become the ultimate time capsule, a message from the universe to itself, whispering across the abyss of time. And that's the paradox at the heart of it all. The universe, in its final act, might preserve every secret it ever held, but only if there's someone or something left to listen. The light that escapes the end won't just be a relic. It'll be a test, a challenge to whatever remains to prove that even in the face of oblivion, the story doesn't have to end. The information is there. The question is, will we ever be able to hear it? The idea of a multiverse, that our universe might be just one bubble in an infinite cosmic foam, isn't just science fiction. It's a serious hypothesis born from the math of quantum mechanics and string theory. But if other universes exist beyond our own, what happens to the light struggling to escape our dying cosmos? Could it slip through some hidden crack in reality, crossing into another universe entirely? Or are we trapped in a solitary fate, destined to fade without ever touching another world? Picture this: our universe is a sinking ship, slowly submerging into the void. Light is the last signal flare, fired into the darkness in hopes of reaching another vessel. In a multiverse scenario, that flare might not just vanish, it could breach the boundary between worlds. The concept hinges on the idea that universes aren't perfectly sealed. Quantum fluctuations, cosmic inflation, or even black hole singularities might create fleeting bridges, wormholes, or quantum foam, where particles, including photons, could tunnel from one reality to another. It's like light seeping through the pores of a cosmic membrane, escaping into the unknown. But here's the catch. Even if light could cross into another universe, would it mean anything? The laws of physics there might be utterly alien. A photon arriving in a universe with different constants where the speed of light is faster, or electromagnetism behaves unpredictably, could dissolve into noise, its message scrambled beyond recognition. The light that escapes might not be a beacon at all, just a faint ripple lost in an incomprehensible sea. Then there's the darker possibility, isolation. If the multiverse is a vast archipelago of disconnected realities, each sealed in its own pocket of spacetime, then no light, no information, nothing from our universe could ever reach another. The dying embers of our cosmos would flicker out unseen, a private ending with no witnesses beyond our own. This isn't just loneliness on a cosmic scale, it's existential silence, the idea that even in a multiverse we might be utterly alone. Yet some theories offer a sliver of hope. If universes are born from the collapse of previous ones, like phoenixes rising from the ashes, then the light escaping our end could seed the beginnings of another. The photons that slip away might become the first whispers of a new Big Bang, their energy igniting the next cycle of creation. In this way, light wouldn't just be escaping, it'd be recycling, carrying fragments of our universe's story into the next. The truth is, we don't know. The multiverse remains a tantalizing what if, a canvas for our biggest questions and boldest speculations. But whether light can cross the divide or not, the idea forces us to confront something profound. The universe's end might not be an ending at all. It could be a transformation, a passing of the torch, or just one quiet note in an endless symphony of realities, each living, dying, and echoing in ways we're only beginning to imagine. Neutrinos are the universe's ultimate escape artists, tiny, nearly massless particles that slip through entire planets like they're not even there. Born in the hearts of stars, the fury of supernova, and the violent collisions of black holes, these ghostly particles barely interact with matter at all. While light gets absorbed, bent, or blocked by the cosmic structures in its path, neutrinos sail straight through, untouched and unfazed. In a dying universe where even the most stubborn photons are stretched into oblivion, neutrinos might be the last particles still moving, still carrying whispers of a cosmos that once blazed with energy. Take the sun, for example. Every second, trillions of neutrinos zip through your body, remnants of nuclear fusion reactions in its core. You don't feel them. Your walls don't stop them. Even a slab of lead light-years thick wouldn't block more than a handful. This near invulnerability to obstruction means that long after the last stars have burned out, long after black holes have evaporated, neutrinos will still be drifting through the void, unchanged, unfiltered, and utterly indifferent to the universe's demise. But here's where it gets fascinating. Unlike light, which redshifts and fades as space stretches, neutrinos don't lose their energy the same way. Their tiny mass and lack of electromagnetic interaction mean they're immune to many of the forces that cripple photons over cosmic distances. Even as the universe expands into a cold, dark expanse, these particles will keep their original signatures, their speed and energy reflecting the conditions of their birth billions of years earlier. Imagine finding a letter written at the dawn of time, its ink never fading, its words never blurring. That's the promise of neutrinos in the far future. Yet their elusiveness is also their curse. Detecting neutrinos today is like trying to catch smoke with your bare hands. Our most sophisticated observatories, giant tanks of water or ice buried deep underground, only catch a fraction of the neutrinos passing through. In a future where stars no longer shine and light is all but gone, how would any surviving civilization detect these ghostly messengers? The answer may lie in their sheer persistence. Over unfathomable timescales, even the rarest interactions could add up. A single neutrino, after traveling for trillions of years, might finally collide with an atom in some forgotten detector, sparking a signal in the darkness. And that signal could be priceless. Neutrinos from the early universe carry pristine information about the moments of their creation, unchanged by the chaos of cosmic evolution. They could tell us about the cause of the first stars, the explosions of ancient supernova, or even the violent birth cries of black holes we'll never see again. In a sense, they're cosmic time capsules holding data that light, warped and redshifted beyond recognition, can no longer preserve, but there's a deeper question lurking here. If neutrinos truly outlast everything else, could they be the final keepers of the universe's story? Long after the last black hole has evaporated and the cosmic microwave background has faded to nothing, neutrinos might still drift through the void, their faint trails encoding the history of everything that ever was. The universe's epitaph wouldn't be written in light, it'd be etched in these ghostly particles, a testament to existence so resilient it refuses to vanish even in eternity's grip. So while light may be the universe's most eloquent storyteller, neutrinos could be its last, silent, nearly undetectable, but enduring long after everything else has faded into the dark. They're the universe's final whisper, a message in a bottle tossed into an endless sea, waiting for someone or something to finally read it. Imagine the universe in its final state, cold, dark, and nearly empty. Atoms are so far apart they might as well be isolated islands in an endless sea of nothingness. Time stretches on for eternity with no stars, no planets, just the faintest whisper of radiation fading into the void. Yet in this desolate expanse, something impossible happens. A random fluctuation in the quantum foam, a tiny blip of order in an ocean of chaos, briefly assembles a fully conscious mind. This is the Boltzmann brain, a self-aware entity born from pure chance, existing just long enough to ask one terrifying question: am I the last observer in existence? The idea stems from a haunting implication of thermodynamics. In an infinite universe, even the most unlikely events must happen eventually. Given enough time, the random motion of particles could theoretically arrange themselves into any configuration, no matter how improbable, including a functioning brain with false memories of a past that never was. A Boltzmann brain wouldn't be born in a womb or built in a lab. It would simply appear, conjured into existence by the universe's chaotic dance, only to dissolve back into the void moments later. And in that fleeting instant, it might witness the last flickers of light escaping the dying cosmos before vanishing forever. But here's where the paradox cuts deep. If Boltzmann brains are possible, how do we know we aren't them? Our certainty about the past, the Big Bang, the rise of galaxies, the evolution of life, could be an illusion, a false memory generated by random fluctuation. The universe we think we remember might never have existed at all. It's a dizzying thought that you, me, everything we perceive as real, could be nothing more than a momentary glitch in an eternal void, destined to blink out as suddenly as we appeared. Yet there's a counterargument buried in the math. While fluctuations can create order from chaos, the odds of a fully formed brain popping into existence are astronomically worse than the odds of an entire universe evolving naturally. It's like comparing the chance of a hurricane assembling a jet engine from scrap metal to the chance of a factory building one deliberately. The universe we see, with its laws, its constants, its staggering complexity, is far more likely to be real than a hallucination conjured by accident. But let's return to that dying cosmos. If Boltzmann brains do emerge in the far future, their existence would rewrite the rules of observation. Light that's been traveling for trillions of years, stretched and dimmed by the expansion of space, might finally meet its only witness, a mind that shouldn't exist, seeing what no one was meant to see. The last photon escaping a black hole's evaporation, the final ripple of Hawking radiation, the dying gasp of the cosmic microwave background, all observed by an entity that's here one instant and gone the next. It's poetic in the darkest way. The universe's final act isn't silence, but a scream into an empty room, heard only by a listener who never truly was. So where does that leave us? The Boltzmann brain paradox isn't just a thought experiment, it's a mirror held up to our deepest uncertainties about reality, time, and our place in the cosmos. It forces us to confront the unsettling idea that in an infinite universe, even the impossible becomes inevitable. And as we ponder the fate of light in a dying cosmos, we're left with one chilling question. If a tree falls in a forest with no one to hear it, does it make a sound? And if a universe dies with only a Boltzmann brain to see it, did it ever really live at all? The second law of thermodynamics paints a grim picture. Entropy, the relentless march toward disorder, always increases. Left alone, every system, from a steaming cup of coffee to the universe itself, will eventually decay into a featureless equilibrium. But here's the cosmic contradiction. Information, the blueprint of reality, seems fundamentally indestructible. Quantum mechanics insists that information can never be truly lost, not even in a black hole's maw. So which force ultimately triumphs in the dying universe, the chaos of entropy or the persistence of knowledge? Picture a sandcastle on the beach. Entropy is the tide, slowly but surely eroding its towers and walls into shapeless grains. Yet every particle of sand still holds the memory of where it once belonged. The information of the castle's structure lingers, even if scattered. Now scale that up to cosmic proportions. Stars explode, black holes evaporate, galaxies disperse, but the quantum states of every particle, every photon, every ripple in spacetime still encode their history. The universe might be crumbling, but its story isn't being erased, it's being scrambled, diluted, stretched thin across infinity. This tension plays out in the fate of light itself. As photons redshift into oblivion, their energy fades, but their quantum information, their polarization, their phase, their entanglement with other particles remains theoretically intact. It's like burning a book and claiming the information is gone just because the pages are ash. The words might be irretrievable to us, but the underlying information still exists in the arrangement of molecules. Similarly, the last light escaping the universe could carry imprints of its origins, buried so deep in quantum correlations that no conceivable technology could decode them. Yet mathematically, they'd still be there, but entropy doesn't surrender easily. In a heat-dead universe where energy is uniformly smeared across space, information becomes so diffuse it's effectively useless. Imagine shouting into a hurricane. Your voice isn't gone, but the storm's roar drowns it beyond recovery. That's the fate of cosmic information, not annihilation, but obfuscation on a scale so vast it might as well be oblivion. The universe's final moments could be a twisted stalemate, information technically preserved, but locked away in a vault with no key, a puzzle with no solver. There's a haunting beauty in this duality. The laws of physics don't choose between entropy and information, they demand both coexist, locked in an eternal dance. The universe's end isn't a victory for chaos or order, but a transformation into something stranger, a realm where every truth still exists, but no one remains to speak it. And in that silence, light's last whispers might just be the universe's way of leaving the light on, just in case someone or something ever comes looking for answers. Imagine civilizations clinging to existence in the far future, their technology advanced beyond our wildest dreams, their societies adapted to a universe growing colder and darker by the eon. These last observers would inhabit a cosmos unrecognizable to us, a night sky stripped of stars, where the only light comes from the faint glow of black hole evaporation or the dying embers of proton decay. Their existence would be a relentless battle against the fading of everything, a struggle to extract meaning from a reality where time itself has lost its grip. For these far future beings, the universe's final act would unfold in slow motion. The last stars flickered out eons ago, their ashes scattered across light years of emptiness. The galaxies they once called home have dissolved into darkness, their structures erased by the relentless expansion of space. Even black holes, those cosmic titans that outlasted everything else, would be nearing their end, leaking away their mass in faint bursts of Hawking radiation. The only light left would be the dimmest of whispers photons stretched so thin by cosmic expansion that their wavelengths dwarf the observable universe. Yet against all odds, these survivors might still find ways to witness light's last stand. With technology harnessing energies we can't yet fathom, they could build detectors sensitive enough to catch the faintest signals, photons from the final evaporating black holes, the last vestiges of the cosmic microwave background, or even the rare neutrinos still carrying echoes of a vanished stellar era. They'd be like astronomers peering through a telescope at a star that died millennia ago, only now the entire cosmos is their graveyard, and every flicker of light is a message from a past long gone. But here's the heartbreaking twist: even for them, darkness would eventually win. As the universe expands faster and faster, pushing galaxies beyond the horizon of observation, the last photons would redshift into nothingness. The cosmic background radiation, once the signature of the Big Bang, would fade into silence. Black holes would complete their evaporation, leaving no trace behind. The final civilizations, no matter how advanced, would face a sky utterly devoid of light, a perfect, unbroken black. In that eternal night, the last intelligent beings might turn inward, preserving their knowledge in quantum fluctuations or engineered pockets of order. They could become the universe's final archivists, encoding its history into structures that outlast even the dimmest light. Or perhaps they'd accept the inevitable, letting their consciousness dissolve into the void, becoming one with the endless dark. The cruelest irony: even if they witnessed light's last stand, their observations might never be shared. With no one left to hear, no future minds to receive their findings, their discoveries would vanish into the abyss. The universe's final chapter wouldn't just be about the death of light, it would be the death of witnesses. And yet, in that silence, there's a strange kind of poetry. The universe began in fire, bathed in light, teeming with possibility. It ends in cold, in dark, in stillness, but for a fleeting moment, a cosmic blink, there were eyes to see it, minds to comprehend it. The light may fade, but the fact that it was seen at all means the universe, in its dying breath, was known, and in that knowing, however brief, lies a kind of immortality. White holes are one of the universe's most tantalizing what-ifs, black holes, hypothetical opposites, theorized to gush out matter and energy instead of devouring them. While black holes trap everything, including light, white holes would violently expel it, like cosmic fire hydrants blasting radiation into the void. The math allows for their existence, but no one's ever seen one. So if they're real, could they become the last sanctuaries for light in a dying universe? Picture a black hole in reverse. Instead of an event horizon that sucks everything in, a white hole would have a boundary that nothing can cross inward, only outward. Matter, energy, even spacetime itself would erupt from its core, a fountain of creation in a cosmos otherwise sliding toward oblivion. For light struggling to escape an aging universe, these cosmic geysers might offer a final exit route. Photons trapped in the collapse of black holes could re-emerge through their white hole counterparts, ejected into a reality where space is still expanding, where their journey hasn't been stretched into nothingness yet. But here's the catch: white holes defy everything we know about thermodynamics. Black holes form when massive stars collapse, but white holes would require something even more improbable: a reversal of entropy, a spontaneous explosion of order from chaos. The universe tends toward disorder, not rebirth. That's why most physicists dismiss white holes as mathematical curiosities, ghosts in the equations with no physical counterpart. Yet in a cosmos facing heat death, where the rules we know begin to fray at the edges, could the impossible become inevitable? There's a provocative idea lurking in the math. Some theories suggest that when black holes finally evaporate via Hawking radiation, their demise might birth a white hole in another universe or another time. The light and information swallowed over eons could come roaring back out, like a message in a bottle washed ashore after drifting through cosmic seas. If true, white holes wouldn't just be a last hope for escaping photons, they'd be bridges between dying realities and newborn ones, recycling the universe's remnants into something fresh. But let's be clear, this is speculation at the furthest edge of physics. No telescope has ever detected a white hole's radiant outburst, and no experiment has confirmed their existence. They might simply be mirages in the equations, placeholders for symmetries that nature never chose to enact. Yet even as a thought experiment, they challenge our assumptions about the universe's final act. If light can't escape the grip of entropy, could it cheat death by slipping through a backdoor we haven't found yet? The irony is delicious. Black holes, the ultimate cosmic traps, might secretly hold the key to light's survival, not by keeping it prisoner, but by transforming into its opposite at the end of time. Whether white holes are real or just a beautiful fantasy, they remind us that the universe's story might not have a single, simple ending. There could be twists we haven't imagined, escape hatches hidden in the fine print of reality. And if even a single photon finds its way through the story of light, and the cosmos isn't over yet, the Big Rip isn't just an ending, it's an unraveling. Picture dark energy not as a steady force, but as one growing stronger over time, its grip tightening until spacetime itself can't hold together. Galaxies, stars, even the atoms in your body would be torn apart in a final, violent crescendo. This isn't the slow fade of heat death or the quiet evaporation of black holes. It's a cosmic shredding where the fabric of reality is pulled apart at the seams. And in that chaos, light faces its ultimate test. Can anything escape the universe's last scream? The key lies in dark energy's behavior. Right now, it acts like a gentle but relentless push, accelerating the expansion of the universe. But if it intensifies, if its strength grows with time rather than staying constant, the push becomes a pull, then a yank, then a catastrophic rip. First, galaxies would be wrenched from each other, their gravitational bonds no match for dark energy's fury. Then, stars within galaxies would be flung apart, next planets torn from their orbits, then the atoms holding you together, ripped into quarks and electrons. Spacetime itself would fracture, leaving no structure, no cohesion, just a sea of isolated particles drifting in an infinite void. Now, imagine light trapped in this maelstrom. Photons traveling through space would find their paths stretched beyond recognition, not just by expansion but by the violent tearing of the medium they move through. Wavelengths would redshift so drastically that visible light would vanish into radio waves, then into wavelengths longer than the universe itself. But here's the twist: some light might still slip through. In the brief moments before the rip reaches its peak, photons emitted from the last remaining structures, perhaps the final stars or evaporating black holes, could escape the immediate destruction, riding the edge of the expanding catastrophe. Yet even these escapees face a grim fate. With spacetime itself disintegrating, there'd be no stable medium for light to travel through. Photons wouldn't just stretch, they'd be stretched into non-existence, their energy diluted to nothing as the space between their peaks and troughs becomes infinite. The universe's last light wouldn't fade, it would be pulled apart like a sentence written on a rubber band snapped in two. But buried in this nightmare scenario is a strange glimmer of possibility. Quantum mechanics suggests that information can't be destroyed, even by the Big Rip. The light that's torn apart might still encode its origins in some unfathomable way, its data preserved in the quantum foam of spacetime remnants. It's like shredding a letter. The words are scattered, but the ink on each fragment remains. If some future physics could piece those fragments back together, the universe's last light might still tell its story. Of course, that's a staggering if. The Big Rip leaves no observers, no detectors, no one to piece together the fragments. The light that escapes wouldn't be witnessed. It would be a message with no receiver, a signal lost in the static of a dying reality. And yet, the fact that it even tries to escape is a testament to light's resilience. In the face of total annihilation, it refuses to vanish quietly. It fights not to be seen, but to exist at all. So while the Big Rip might be the most violent end the universe could face, it's also the most revealing. In its chaos, we see the limits of light's endurance, the breaking point of spacetime, and the terrifying power of dark energy unchecked. And if against all odds, a single photon outruns the end, it carries with it the universe's final defiance, that even in destruction, something, however faint, remains. The Big Crunch offers a radically different vision of the universe's fate, one where the cosmos doesn't fade into darkness, but collapses in on itself in a fiery rebirth. Imagine the expansion we see today slowing, halting, then reversing as gravity. The silent architect of structure finally wins its billion-year tug of war with dark energy. Galaxies would begin rushing toward one another, their light blue-shifting as space contracts, like a film of the Big Bang played in reverse. Stars once isolated by unfathomable distances would collide, their fusion reignited in a cosmic pressure cooker. Black holes would merge into monstrous singularities, swallowing everything in their path, and at the very end, a singularity hotter and denser than anything since the universe's birth, where the laws of physics as we know them cease to exist. But here's the tantalizing question: what happens to light in this apocalyptic finale? Photons racing toward the crunch wouldn't just vanish, they'd be compressed, their energy funneled into the growing inferno. As space shrinks, wavelengths squeeze shorter, turning infrared into visible light, visible into ultraviolet, and ultraviolet into X-rays. The night sky, once dark and empty, would blaze with a brilliance unseen since the first moments of creation. It's as if the universe, in its final act, becomes its own particle accelerator, smashing light into ever higher energies until even photons can't escape the collapse. Yet there's a breathtaking possibility buried in this chaos. Some theories suggest that the Big Crunch might not be an end at all, but a reset. The singularity at the collapse's heart could rebound, triggering a new Big Bang, birthing a fresh universe from the ashes of the old. In this scenario, light wouldn't just be destroyed, it'd be recycled, its energy woven into the fabric of a new cosmic dawn. The photons that once carried the last whispers of dying stars might re-emerge as the first glow of a newborn cosmos, their journey echoing across cycles of destruction and rebirth. This cyclical universe model, often called the Big Bounce, hinges on quantum gravity, a theory that could smooth the infinite densities of a singularity into a springboard for new creation. Instead of a dead-end collapse, the universe would rebound like a ball hitting an unfathomably dense floor, with all its energy, including light, preserved and repurposed. The last light escaping the crunch wouldn't be a farewell, it'd be a seed, carrying the potential for new galaxies, new stars, and perhaps even new observers to decipher its ancient origins. But the Big Crunch isn't just a theoretical curiosity, it's a mirror held up to our deepest cosmic uncertainties. For decades, astronomers assumed gravity would eventually halt the universe's expansion, until the discovery of dark energy upended that idea. Now, with dark energy's true nature still a mystery, the door remains cracked for alternative fates. Could its influence wane over time, letting gravity regain dominance? Or might some deeper physics, like quantum fluctuations or hidden dimensions, rewrite the rules at the last moment? The answers could determine whether the universe's final light is a swan song or a prelude. One thing is certain: if the Big Crunch is real, the light struggling to escape it carries more than energy. It carries the universe's memory, a story etched in wavelengths and quantum states, waiting to be told again. Whether that story ends in silence or a new chapter depends on forces we're only beginning to understand. And that's the most profound twist of all: the universe's fate, and the fate of its light, might still be written in the stars we've yet to see. Eternal inflation paints a picture of a cosmos far wilder than we ever imagined. Not just one universe, but an endless froth of them, bubbling into existence like a cosmic pot that never stops boiling. According to this theory, our universe might be just one bubble in an infinite multiverse, each with its own laws of physics, its own constants, its own destiny. And here's the mind-bending part: as our universe cools and darkens, new ones could be springing to life right beside us, their big bangs igniting in the unseen depths of the quantum foam. Now imagine the last light escaping our dying cosmos, photons stretched thin by expansion, their energy fading but their quantum information still intact. In eternal inflation, that light might not just vanish into the void. It could cross the boundary between universes, slipping into a newborn reality still hot and dense from its own creation. Like a message in a bottle tossed between islands in an endless ocean, these photons could carry traces of our universe's history into another, imprinting its laws or even sparking the conditions for life anew. But how? The math suggests that the space between universes isn't just empty nothingness, it's a seething false vacuum, a kind of quantum energy field that's constantly decaying and reconfiguring. When a bubble universe forms, it's a pocket where that energy drops to a lower state, releasing a burst of heat and light, a big bang. And in rare, almost miraculous cases, the energy and particles from one universe might tunnel through this unstable foam into another. It's like a cosmic game of telephone, where the last whispers of a dying world could shape the first cries of a newborn one. Of course, the odds are astronomically slim. Most photons escaping our universe would redshift into oblivion long before reaching another bubble's boundary. The distances between universes are incomprehensibly vast, and the quantum walls separating them might be impenetrable. But here's where quantum mechanics throws us a lifeline. If particles can tunnel through barriers in a lab, why not across the multiverse? Even one photon making the leap could, in theory, carry a fragment of our cosmic story into the next cycle. The implications are staggering. If light can cross between universes, then the laws of physics might not be random. They could be inherited. The fine-tuning we observe in our universe, the precise constants that allow stars and life to exist, might not be luck. They could be echoes of a previous cosmos, its last light whispering the recipe for structure into the void. We might be living in a universe shaped in part by the dying embers of another. And that raises a haunting question. If our universe's light can seed another, could we trace our own origins back to a prior reality's final flickers? Are we, in some sense, the afterlife of a cosmos long gone? It's a dizzying thought, one that blurs the line between endings and beginnings, because in eternal inflation, death isn't a full stop, it's a semicolon. The story doesn't conclude. It branches, evolves, reinvents itself in ways we're only beginning to fathom. So while our universe may one day grow cold and dark, its light might still be out there, dancing in the quantum foam, waiting to ignite the next chapter. Not as a ghost, but as a spark, and in that spark the cosmos finds its strangest, most beautiful loophole, the chance to live again. The void isn't truly empty. Even in the deepest, darkest reaches of space where temperatures hover near absolute zero and matter is spread thinner than a single atom per cubic meter, something remarkable happens. Quantum fluctuations, tiny bursts of energy borrowed from nothingness, flicker in and out of existence like fireflies in a blackened sky. These fleeting disturbances in the quantum vacuum aren't just mathematical quirks. They're the universe's way of proving that true nothingness might not exist at all. And in the dying cosmos, where every star has burned out and every black hole has evaporated, these ghostly flickers could become the last source of light the universe ever knows. Take the Casimir effect, a phenomenon we've observed right here on Earth. Place two uncharged metal plates incredibly close together in a vacuum, and they'll be pushed toward each other by an invisible force. Why? Because the space between them is too narrow for certain quantum fluctuations to occur, while the space outside remains teeming with them. The result? A slight but measurable pressure proof that the quantum vacuum isn't passive. It's alive with potential, a seething ocean of virtual particles that pop into and out of existence so quickly we can't see them directly. But their influence is undeniable. Now fast forward trillions of years. The universe is a vast, lightless expanse, its energy so diffuse that even atoms struggle to hold themselves together. Yet in this desolation, quantum fluctuations persist. Virtual particle pairs, electrons and positrons, quarks and antiquarks still emerge from the void, dancing for a fraction of a moment before annihilating each other. Normally, these events cancel out perfectly, leaving no trace. But in the bizarre physics of the far future, where spacetime itself is stretched to its limits, something extraordinary could happen. A fluctuation might borrow just enough energy from the vacuum to avoid immediate annihilation, creating a particle with real, measurable existence. And when that particle collides with another or decays, it could emit the faintest glimmer of light, a photon born not from stars or fire, but from the raw instability of empty space. This isn't science fiction. We've seen hints of it in laboratories studying Hawking radiation, where black holes are theorized to create real particles from quantum fluctuations near their event horizons. In a universe stripped of all conventional energy sources, the same mechanism could play out on a cosmic scale. The quantum vacuum, once a silent backdrop, might become the stage for light's final act. And while these photons would be achingly faint, more like the memory of light than light itself, they'd carry a profound message that even in the void, creation never truly stops. But there's a haunting catch. Quantum fluctuations don't produce light predictably or evenly. They're random, sparse, and fleeting. For every photon that escapes annihilation, countless others vanish without a trace. The last light in the universe wouldn't be a steady glow, but a sporadic flickering like embers sputtering in the wind. And with no observers left to witness it, these final flashes would illuminate nothing but the dark. Yet in their randomness lies a strange kind of poetry. The universe began in a firestorm of quantum fluctuations during the Big Bang. It might end with their quiet return, not as a cataclysm, but as a whisper. A reminder that even at the end of time, the fabric of reality refuses to sit still. That light, in its purest form, isn't just something the universe has, it's something the universe is. And whether anyone's left to see it or not, that light will keep fighting, flickering and fading, until the very last quantum fluctuation winks out of existence and the cosmos finally knows true silence. Red dwarfs are the universe's marathon runners, small, cool stars that burn so slowly they could outlast every other object in the cosmos. While massive stars blaze brightly and die young in spectacular supernova, these dim crimson embers sip their hydrogen fuel over trillions of years, clinging to life long after galaxies have faded to black. Picture the far future where the Milky Way's spiral arms have dissolved, where black holes have evaporated, and the only light left comes from these stubborn survivors, scattered like dying campfires in an endless night. But even red dwarfs aren't eternal. Their fuel, though carefully rationed, will eventually run dry. As the last generation of stars, their deaths mark the true end of stellar light in the universe. The process is slow and undramatic. Unlike their giant cousins, red dwarfs don't explode. Instead, they gradually cool into black dwarfs, dark stellar corpses radiating only the faintest heat into the void. The transition is so gradual that by the time the last red dwarf flickers out, the universe will already have been dark for eons, its expansion having carried all other light beyond the horizon of detection. Yet in their final moments, these last stars could offer one final cosmic spectacle. As their cores exhaust the last traces of hydrogen, they might undergo a subtle transformation, their outer layers puffing into delicate planetary, nebulae, ghostly halos of gas illuminated by the dying star's fading ultraviolet glow. For a brief cosmic moment, these nebulae would shine like beacons in the darkness, their intricate patterns visible to any remaining observers. But with no new stars to ignite, these glowing shells would dissipate into the void, leaving behind only the cold, dark remnants of the star's core. What's truly haunting is the timescale. The universe today is only 13.8 billion years old, a fraction of the lifespan of the smallest red dwarfs. By the time the last of them dies, the cosmos could be quadrillions of years into its future, a period so vast it makes the current age of stars seem like the blink of an eye. Civilizations, if any still exist, would look up to a sky devoid of constellations where the concept of a star is a relic of ancient history. The very idea of a galaxy, once the fundamental unit of cosmic structure, would be a distant memory, its stars scattered beyond recognition by the relentless expansion of space. But here's the twist: red dwarfs might not be entirely alone in their vigil. Brown dwarfs, failed stars too small to sustain full fusion, could linger even longer, their faint infrared glow persisting long after true stars are gone. And rogue planets flung from their orbits by gravitational interactions might still drift through the void, warmed only by the residual heat of radioactive decay in their cores. These dark, wandering worlds could become the last refuges for any surviving life, huddling around geothermal vents in oceans buried under miles of ice. The death of the last star isn't just the end of light, it's the end of an era. For billions of years, stars have been the engines of cosmic change, forging heavy elements in their cores, shaping galaxies with their births and deaths, and providing the energy that made life possible. When they're gone, the universe becomes a very different place, one where the only sources of energy are the slow decay of black holes and the faint whisper of quantum fluctuations. It's a future so distant it's almost unimaginable, yet it's written into the laws of physics as surely as the Big Bang itself. And so, the last star doesn't just fade, it closes a chapter. Its death is the universe's quiet farewell to the age of light, a transition from a cosmos teeming with energy to one where darkness reigns. But even then, the story isn't quite over. Because in the cold and the dark, the universe still has one last trick up its sleeve, a final, flickering spark that could outlast even the longest-lived star. Black holes aren't the eternal prisons they seem to be. They're ticking clocks, counting down to their own explosive finales. Thanks to Hawking radiation, these cosmic giants slowly leak energy over eons, shrinking until they vanish in a final, blinding flash. But here's the twist: that flash might be the last meaningful light the universe ever produces. Imagine a cosmos so old that stars are extinct, galaxies have dissolved, and space is colder than absolute zero. The only remnants, a handful of ancient black holes, each glowing faintly as they evaporate into the void. Their deaths won't be quiet. When a black hole's mass dwindles to about 1 million metric tons, it unleashes energy equivalent to 1 billion nuclear bombs in a fraction of a second, a farewell firework visible across the dying universe. This isn't just theoretical. Hawking radiation arises from quantum mechanics' strangest quirk, particle-antiparticle pairs constantly popping into existence near the event horizon. Normally, they annihilate instantly, but if one particle falls into the black hole while the other escapes, the whole loses mass. Over time, this trickle becomes a flood. The smaller the black hole gets, the faster it evaporates, its temperature skyrocketing until it reaches a catastrophic climax. For a primordial black hole, one formed in the chaos of the early universe, that moment could be happening right now, somewhere in the cosmos. For the supermassive ones at galactic centers, they'll outlast nearly everything else, their final burst trillions of years in the future. But here's the haunting question: who's left to witness it? By the time the last black holes explode, the universe will be unrecognizable. Space will have expanded so much that even neighboring black holes are isolated by unimaginable distances. Their dying light, though brilliant, will redshift into near nothingness, stretched by the relentless expansion of spacetime. Any hypothetical observers would see not a flash, but a slow fade, a single photon arriving every millennium, each carrying less energy than a whisper. It's a bitter irony. The universe's last light show might play to an empty theater. Yet even in this bleak scenario, there's a glimmer of cosmic poetry. Hawking radiation isn't just heat, it's information. According to quantum theory, the particles escaping a black hole carry traces of what fell in, scrambled but not destroyed. Those final bursts could be the universe's last act of storytelling, encoding the history of everything the black hole ever consumed. The light from a dying black hole might not just be energy, it could be a message, a final testament to a cosmos that refused to let its secrets die quietly. So while these explosions mark the end of an era, they also hint at something deeper. The universe, even in its coldest, darkest hours, finds ways to be remembered. Whether anyone's left to listen is another story, but the light will shine anyway, a defiant spark in the infinite night, proving that existence, no matter how fleeting, leaves echoes that outlast even time itself. The cosmic microwave background is the universe's oldest photograph, a snapshot frozen in time when the cosmos was just 380,000 years old, a seething plasma of particles cooling enough to release their first light. Today, that glow has stretched into microwaves, a faint whisper detectable only by the most sensitive radio telescopes. But like all light in an expanding universe, it's fading. Every second, as space stretches further, Those primordial photons redshift into longer, weaker wavelengths, their energy dissipating into the void. One day, far in the future, even this echo of creation will vanish entirely, leaving the cosmos without its most fundamental anchor to the past. What happens when that anchor is gone? For cosmology, the cosmic microwave background isn't just a relic, it's a Rosetta Stone. Its subtle temperature variations, mapped in exquisite detail by satellites like Planck, reveal the seeds of all cosmic structure, the slight overdensities that grew into galaxies, the fingerprints of dark matter's gravitational scaffolding, even the echoes of inflation's explosive birth. Without it, we'd be blind to the universe's infancy, forced to reconstruct its early moments from scattered clues like detectives piecing together a crime scene with half the evidence missing. But the cosmic microwave background's fading isn't just a loss of day, it's a transformation of the cosmos itself. As its light dims, the universe loses its last tether to the era before stars. Future civilizations, if any exist, will gaze into a sky devoid of this primordial glow, with no direct evidence that a Big Bang ever happened at all. They might infer it from the expansion of space or the abundance of light elements, but the smoking gun, that uniform microwave whisper, will have dissolved into silence. The universe's origin story, once written in photons, will become a legend passed down through equations rather than observation. There's a haunting beauty to this inevitability. The cosmic microwave background is the universe's way of remembering its birth, a keepsake carried across billions of years. Its eventual disappearance marks the moment the cosmos truly grows up, stepping out of the shadow of its creation and into a future unmoored from its past. And yet, even as it fades, it leaves behind a paradox. The more the universe forgets, the more we've learned. Every subtle fluctuation in that ancient light has taught us about dark energy, neutrino masses, and the geometry of spacetime, lessons that will outlast the glow itself. Perhaps that's the ultimate lesson of the cosmic microwave background. The universe doesn't need to cling to its history to make it meaningful. The light may vanish, but the knowledge it gave us, the understanding of where we came from and how everything began, will endure as long as there are minds to ponder it. And in that way, the afterglow of the Big Bang never truly fades. It just changes form, from photons in the void to ideas in the dark. Right now, we're bathing in the glow of the observable universe, light from galaxies billions of light years away still reaching us, carrying stories from the cosmos's youth. But that golden age of observation won't last. The universe's expansion isn't just stretching space, it's accelerating, pushing galaxies apart faster than their light can bridge the gap. One day, distant galaxies will vanish from view, not because they've died, but because the space between us is growing too quickly for their light to keep up. It's like watching a ship sail over the horizon, except this horizon isn't fixed, it's racing outward, swallowing more of reality with every passing second. Consider the fate of a galaxy 10 billion light-years away. Today, its light reaches us, telling tales of a younger cosmos. But as space expands, the distance between us grows at a rate that eventually outpaces light's ability to cross it. The galaxy isn't moving away through space, space itself is stretching, carrying the galaxy along like a leaf on a rushing river. Eventually, the river flows so fast that the leaf disappears downstream, its light stretched into wavelengths too long to detect, its signal lost in the cosmic static. Future astronomers, no matter how advanced their tools, will never see that galaxy or the countless others that slip beyond the horizon. This isn't just about losing a few distant points of light. It's a fundamental reshaping of reality's boundaries. The observable universe is shrinking, not because the cosmos is getting smaller, but because the reachable portion of it is. Civilizations born billions of years from now will inherit a far lonelier cosmos, their night skies stripped of all but the closest galaxies. They might never know the universe was once teeming with galaxies, or that it began in a fiery Big Bang. The evidence will have literally drifted out of sight, leaving them with a sky that tells only half the story. The irony is brutal. We live in a privileged sliver of cosmic time, late enough to see the universe's structure, early enough to still witness its origins. The cosmic microwave background, the redshift of distant supernova, the large-scale web of galaxies, all these clues are fleeting. In a trillion years, they'll be gone, erased by expansion. Future scientists might deduce the universe's history through painstaking indirect evidence, but they'll never see it firsthand. It's as if we're standing on a shoreline at low tide, documenting the exposed seabed, while future generations arrive only after the waves have risen, forever unaware of what lies beneath. But here's the twist: the horizon isn't just stealing the past, it's hiding the present. Right now, events are unfolding in galaxies so distant that their light will never reach us, no matter how long we wait. Entire civilizations could rise and fall, stars could explode in spectacular supernova, and we'd never know. The observable universe isn't just a window, it's a cage, forever limiting what we can see, hear, or comprehend. Does that mean reality is bigger than what we perceive? Almost certainly, but how much bigger, and what lies beyond our horizon? The truth is, we'll never know. The universe's expansion is a one-way curtain, closing on vast swaths of existence before we even get a chance to look. And that raises a chilling possibility. If we're already cut off from parts of reality, how much have we lost already? The cosmos might be infinitely richer than we imagine, but we're forever stranded on an island of observation, watching as the tides of expansion carry the rest away. What does it mean for existence to end, not just for a star or a galaxy, but for reality itself? If the universe were a story, its final chapters wouldn't be written in fire or ice, but in light's quiet struggle to outrun oblivion. And that raises a question far deeper than physics. When the last photon escapes, what is it carrying? Not just energy, not just information, but something more elusive: the weight of being. The idea that light might be the universe's final witness forces us to confront an unsettling truth. Memory isn't just a human concept. It's woven into the fabric of reality, etched into the paths of particles and the echoes of entropy. Think of the last light from a dying star, red shifted into near nothingness as it crosses an expanding cosmos. That photon doesn't just carry data about the star's composition or temperature. It carries the fact of the star's existence, a proof that it burned, that it mattered, that it was here. In a universe hurtling toward heat death, where time stretches into meaningless eternity, light becomes more than a messenger. It's a cosmic scribe, recording events for no one, preserving history without an audience. This isn't just science, it's metaphysics. If a tree falls in a forest with no one to hear it, the sound still ripples through the air. If a universe dies with no one to remember it, does its light still whisper? Philosophers have wrestled with the idea of qualia, the subjective experience of being. But what about cosmic qualia? The universe in its final act might not have consciousness, but it has persistence. Light's escape is a refusal to surrender, a defiance of the void. Every photon that slips free is a vote against erasure, a tiny rebellion against the idea that existence is fleeting, and in that rebellion there's a strange comfort. Even if no mind ever deciphers the message, the universe leaves a record, not in stone or ink, but in the immutable language of physics. Yet here's the paradox: memory requires a frame of reference. Without an observer, does the universe's story still count as a story? Or is it just noise, a random arrangement of particles with no meaning attached? Some theories suggest that quantum entanglement, the way particles remain connected across distances, might preserve correlations, a kind of cosmic memory even in the absence of minds. If true, the universe's final light could be less like a dying breath and more like a fingerprint, an imprint of everything that ever was, waiting in the dark for a reader who may never come. The terrifying beauty of this idea is that it renders the universe both tragic and transcendent. Tragic because all its grandeur, its galaxies, its civilizations, its art and violence and love might one day exist only as faint tremors in long-dead light. Transcendent because in those tremors the cosmos achieves a kind of immortality, not the immortality of gods or souls, but of structure, of patterns that refuse to dissolve. The light that escapes doesn't just tell us how the universe died, it tells us how it lived, and in that telling, even a dying universe proclaims the most human of truths: to exist is to leave a mark. Right now, the James Webb Space Telescope is capturing light from galaxies so distant. Their light has traveled over 13 billion years to reach us, giving us a window into the universe's infancy. But as the cosmos evolves toward its eventual demise, how will scientists of the far future study an era where stars have burned out, galaxies have dissolved, and light itself is fading? The challenge isn't just technological, it's existential. Future astronomers won't just need better telescopes, they'll need entirely new ways of seeing. Consider the tools we rely on today. Our greatest observatories detect visible light, radio waves, X-rays, all forms of electromagnetic radiation. But in a universe where expansion has stretched most photons into undetectable wavelengths, traditional astronomy hits a wall. The last visible stars might vanish within 100 trillion years, leaving behind only the faint infrared glow of cooling stellar remnants. By then, the cosmic microwave background, our snapshot of the Big Bang, will have redshifted into oblivion, its once revealing whispers dissolved into silence. Future researchers won't have the luxury of looking backward. Their only clues will come from the slow, subtle processes that persist in the dark, the quantum evaporation of black holes, the rare decay of protons, or the faint thermal echoes of long-dead stars. This raises a radical possibility. The astronomers of the far future might abandon light altogether. Instead of telescopes, they could build detectors tuned to gravitational waves, ripples in spacetime from the final collisions of black holes or the vibrations of cosmic strings. These waves don't redshift like light. They carry information unimpeded by the expansion of space. Imagine a civilization mapping the universe not by photons, but by the tremors of spacetime itself, reconstructing cosmic history from the echoes of ancient collisions. But even gravitational waves have limits. As black holes evaporate and cosmic activity slows, the universe grows quieter. The last detectable events might be the final pops of evaporating primordial black holes, each a brief burst of radiation in an otherwise silent void. To study these, future scientists might deploy quantum sensors so precise they can detect the faintest spacetime disturbances, or networks of self-replicating probes drifting between galaxies, cataloging the last traces of heat in an ever-cooling cosmos. The real breakthrough, however, might lie in decoding the universe's hidden archives. Dark matter, though invisible, could retain gravitational imprints of long-vanished structures. Neutrinos, those ghostly particles that barely interact with matter, might still carry unredshifted signals from the universe's stellar heyday. And if protons decay, as some theories predict, their rare, slow disintegration could become a new cosmic clock, ticking through the darkness long after light has faded. Yet the greatest obstacle isn't just observation, it's time. Human-scale projects won't cut it in a cosmos where processes unfold over quadrillions of years. Future science might rely on autonomous AI, programmed to patiently collect data across epochs no biological mind could witness. Or perhaps civilizations will engineer their own longevity, slowing their perception of time to match the universe's glacial decay. The irony is profound. We're living in the universe's golden age of observation, where light still carries stories from every corner of spacetime. But the far future holds its own kind of revelation, not by looking outward, but by listening deeper, probing subtler signals, and piecing together a cosmos that no longer shines, but still stubbornly refuses to be forgotten. Could civilizations outwit the universe's death? Imagine a society so advanced that they've transcended stars, building megastructures around black holes to harvest their Hawking radiation, a final, desperate power source in a light-starved cosmos. These wouldn't be the sleek cities of science fiction, but grim outposts clinging to the last usable energy in existence, their existence pared down to the bare essentials of computation and survival. Their artificial light engineered photons from quantum reactors or the faint glow of black hole accretion disks might flicker long after nature's last star has burned out, becoming the final beacons in an otherwise lightless void. The physics of such a civilization stretches our understanding of engineering to its limits. Black holes, especially the supermassive ones at galactic centers, could serve as cosmic batteries. By capturing the energy of their Hawking radiation or siphoning power from their spin via theoretical constructs like Penrose processes, a civilization could eke out existence for epochs beyond imagining. But here's the catch: even these power sources dwindle. As black holes evaporate, their energy output surges briefly before vanishing entirely, a final, unsustainable spike. The last intelligences might find themselves trapped in a cruel paradox. The more energy they extract, the faster their power supply disappears, like drinking from a glass that shatters as you drain it. Quantum energy offers another sliver of hope. In the far future, when space is too diffuse for conventional energy production, civilizations might tap into zero-point energy, the seething quantum fluctuations of the vacuum itself. Theoretically, this energy is inexhaustible, woven into the fabric of spacetime, but harnessing it isn't like flipping a switch. It would require technology operating at scales we can barely conceive, manipulating spacetime like clay to extract usable power. Even if possible, the energy yield might be vanishingly small, forcing civilizations into extreme austerity, their societies optimized for minimal energy expenditure, their cultures reshaped around the dogma of conservation. Yet the most haunting question isn't whether such survival is possible, it's whether it's meaningful. A civilization enduring in the frozen depths of the far future would face existential solitude. With galaxies scattered beyond contact, their night skies utterly black, their history reduced to fragments in quantum memory, could they even remember what it meant to live under a sun? Their artificial light might outlast the cosmos, but it would illuminate nothing but the walls of their own confinement, a flickering candle in an infinite vault. And then there's the ultimate limit, time itself. In a universe marching toward heat death, even the most resilient systems decay. Quantum fluctuations might spawn random moments of order, Boltzmann brains, temporary pockets of consciousness, but these are phantoms, not continuity. The last civilization's light, no matter how ingeniously sustained, would eventually gutter out, leaving no one to remember it had ever shone. But perhaps that's the point. The universe doesn't need witnesses to justify its existence. The mere fact that, against all odds, something once burned bright in the dark, whether a star or a soul or a machine's cold glow, might be enough. The last light wouldn't be a lament, it'd be a declaration we were here, and for a little while longer we refuse to let the dark win. The universe is dying. Not today, not tomorrow, but inevitably, irreversibly. One day every star will burn out, every black hole will evaporate, and the cosmos will fade into an eternal, frozen dark. So here's the uncomfortable question. If nothing lasts, does anything truly matter? It's a dilemma that's haunted philosophers and physicists alike, threading through human history like a shadow. The ancient Stoics wrestled with impermanence, finding purpose in virtue despite life's fleeting nature. Modern cosmologists confront the same void, armed not with poetry but equations. The answers they're uncovering challenge our deepest assumptions about meaning, legacy, and why existence even bothers to spark in the first place. Consider a star. It burns for billions of years, forging atoms in its core, seeding planets with the ingredients for life, then dies in a cataclysm that scatters those elements across space. Its light travels for eons, only to dissolve into the cosmic background. No one remembers its name, no monument marks its passing, and yet without that anonymous sacrifice, life as we know it wouldn't exist. The star's meaning isn't in its memory, but in its consequence. The universe doesn't keep score, it simply unfolds, one act of creation and destruction feeding the next. This shifts the ethical lens. If meaning isn't tied to permanence, then a dying universe isn't a tragedy, it's a canvas. The civilizations that rise, the art they create, the connections they forge, none of it is cheapened by the knowledge that one day the last light will fade. In fact, the opposite might be true. Impermanence heightens value. A flower pressed between the pages of a book is precious precisely because it won't last. The universe, in its slow march toward entropy, becomes a vast gallery of fleeting masterpieces, each moment irreplaceable precisely because it can't be repeated. But there's a counterargument lurking in the dark. If nothing endures, doesn't that render effort meaningless? Why build, why explore, why love, if the universe itself is a sinking ship? This is where science and philosophy collide. Physics tells us the end is inevitable, but it also reveals a startling truth. The universe is a storyteller. Light carries information across time. Black holes encode it in their Hawking radiation. Quantum fluctuations preserve it in the vacuum. The cosmos might be doomed, but it's also relentless in its refusal to erase itself completely. So perhaps the real question isn't whether meaning survives the universe's death, but whether meaning ever required survival to begin with. A symphony isn't worthless because the final note fades. A fire isn't pointless because it burns down to embers. The value is in the doing, the being, the witnessing, not the aftermath. The universe, in all its transient glory, might be the ultimate testament to that idea. A reminder that meaning isn't found in the destination, but in the brilliance of the journey itself. And that's the paradox at the heart of existence. The universe's mortality doesn't diminish our place in it, it defines it. We're here because stars died. We're here because space expanded. We're here because against impossible odds, light kept fighting its way through the dark. The end isn't an erasure, it's the frame around the painting, the silence after the music, the thing that makes the whole story worth telling in the first place. So should we care about a universe doomed to die? The answer might be simpler than we think. We already do, because caring is what makes the journey matter. And in the end, that's all there ever was. As we trace the path of light fleeing a dying universe, we're left staring into a mirror that reflects our own fragile existence. Every photon that slips free carries more than energy. It carries a testament to the universe's stubborn refusal to vanish without a trace. Think of the light from a long dead star still traveling across the void, its journey outlasting the star itself by billions of years. In that simple act of persistence, there's a profound metaphor. Even as the cosmos unravels, it insists on being remembered, if only by the faintest imprint on the fabric of spacetime. This isn't just physics, it's poetry written in the language of entropy. The universe's final light won't just fade, it'll stretch, redshift, and dissolve, but its quantum signature lingers, a whisper locked in the equations of reality. Some theories suggest that even in heat death, information persists, scrambled but never lost. It's as if the cosmos, knowing it can't escape its fate, settles for leaving behind a puzzle no one may ever solve. And that raises a hauntingly beautiful question. Does a story still matter if there's no one left to read it? Yet here's the twist, we are reading it now. Our ability to ponder these questions, to trace light's escape and decode its secrets, transforms the universe's finale from a tragedy into a revelation. The same laws that doom the stars grant us the fleeting gift of witnessing them. For a brief cosmic moment, we're the universe's way of understanding itself, of finding meaning in the very forces that will one day erase us. That paradox that our impermanence is what makes our curiosity so extraordinary is the heart of the mystery. So what does the last light reveal? Perhaps not answers, but a deeper appreciation for the questions. Every sunset, every glimmer of starlight, every beam escaping a black hole's grip is a reminder that existence is a rare and temporary spark in the dark. The universe's story doesn't need an eternal audience to be meaningful. It simply is, a fleeting, glorious phenomenon that, for a blink of cosmic time, included us. As you click away from this video, take that perspective with you. The next time you see a sliver of moonlight or the glow of a street lamp, remember, you're witnessing the same defiance that will one day play out on the grandest scale. Light's escape isn't just a cosmic event, it's a mirror, and in that reflection we see our own brief, brilliant dance against the dark. If this journey through the cosmos's final act resonated with you, let's keep the conversation alive. Drop a comment below. What part of light's great escape left you in awe? And don't forget to like and subscribe for more deep dives into the mysteries that shape our universe. After all, the story isn't over yet, not by a long